So picture a multi-million-dollar industrial turbine.
Right, a massive piece of equipment.
Exactly. I mean, we are talking about an absolute titan of engineering, heavy steel machinery that literally powers a whole city grid, or maybe runs a sprawling petrochemical refinery, or, drives a massive mining operation.
Yeah, these things are incredibly loud, super powerful, and they're built to withstand extreme operational stress.
Right. But now imagine that exact same mechanical giant just being brought to its knees, forced into this catastrophic screeching shutdown by a single drop of water, or like a fleck of dirt you can't even see without a microscope.
It's wild. The contrast is staggering. You have hundreds of tons of steel spinning at thousands of revolutions per minute, completely at the mercy of these microscopic variables.
Which is exactly our mission for today's deep dive. We are stepping into the incredibly high stakes and honestly kind of invisible world of industrial fluid management.
And we've got some great material to work from today.
We do. We've got a stack of sources in front of us provided by Clean Oil Services, and these aren't just, standard marketing brochures.
No, definitely not.
We are looking at highly detailed technical summaries, operational workflow documents, and some very revealing, honestly, sometimes shocking field photography.
Yeah, what's fascinating here is that in the world of heavy industry, whether it's power generation, utilities, or oil and gas, the machinery is fundamentally only as reliable as the molecular cleanliness of the fluid running through its veins.
Molecular cleanliness, that's intense.
Right. Everyone understands the concept of getting an oil change for a passenger car. But at this massive industrial scale, the goal isn't just swapping out old fluid for new. It is absolute, verified contamination control.
Which means we really have to start by looking at the oil itself. And I have to admit, looking through these documents, the most surprising takeaway for me was something the industry calls the new oil paradox.
Oh yeah, this catches so many people off guard.
Because, if you have a dirty system, logic dictates you just buy brand new oil, crack open the sealed drum, and pour it right in.
It makes sense intuitively.
Right. But the sources state very clearly that brand new oil, straight from the supplier, is simply not clean enough to use in sensitive industrial systems.
It is a massive blind spot for a lot of operations. The technical distinction the sources make here is really crucial to understand. New oil from a bulk supplier meets what are called API performance specifications.
Okay, so what does that actually mean?
It means it has the correct viscosity, the right chemical base, and the necessary additive packages for whatever job it's meant to do. But it wildly fails ISO cleanliness standards.
Okay, let's unpack this because, if I buy a brand new gallon of milk, I expect it to be pure. I'm not expecting dirt in it.
Right.
So why is this expensive, highly engineered industrial oil showing up full of microscopic junk? Pouring that into a turbine feels like eating a gourmet meal off a filthy plate you found in a dusty warehouse. And what exactly is this ISO standard it's failing?
Well, let's break down the ISO standard first, specifically ISO 4406. Is the international standard for measuring particulate contamination in fluids.
Okay.
And instead of just looking at a sample and saying, that looks clean, ISO 4406 uses lasers to actually count the number of microscopic particles in a single milliliter of fluid.
Wow, lasers.
Yeah, it specifically counts particles at 3 sizes: 4 microns, 6 microns, and 14 microns.
Just to give you some context on that, a single human hair is about 70 microns thick.
Right.
So we are talking about counting particles that are 10 to 15 times smaller than the width of a human hair.
Exactly. And high-tech hydraulic systems and turbines require an incredibly strict, very low ISO code to operate safely. But the oil arriving from the supplier usually has a very high failing ISO code.
So why is it so dirty if it's brand new?
It comes down to the reality of the supply chain. During bulk production, the oil picks up microscopic metalware particles from the manufacturing equipment itself.
Oh, from the factory making it?
Yeah. Then it goes into rail cars or tanker trucks, which are, rarely pristine. And finally, it sits in metal drums in outdoor storage yards, expanding and contracting with the weather, pulling in condensation and shedding interior rust from the drum right into the oil.
But why does the industry tolerate that? Why don't the oil manufacturers just clean it before they ship it?
Honestly, it's purely economics. They are producing millions of gallons of a bulk commodity, not some highly refined pharmaceutical-grade chemical.
Oh, that makes sense.
If they had to filter every single barrel to a microscopic ISO turbine standard, the cost of the oil would just be astronomical. So they leave the final polishing up to the end user.
And the danger is that end users often just don't realize they are supposed to do that. Like, I'm looking at a photo from the field files right now. It's a picture of a white plastic bucket.
Oh, I know the one.
Yeah, the top half of the liquid is this clear golden oil, but the bottom half is a dark, almost black, thick sludge. It is really jarring to realize this kind of degradation and debris is just hiding in a brand new drum, waiting to be poured into a piece of equipment that costs $50 million.
Yeah, if a plant manager simply assumes new equals clean and introduces that standard barrel oil into their system, they are actively injecting abrasive wear into their machinery from day one.
That's terrifying.
It really is. In modern turbines, you have high-speed bearings and servo valves with clearances tighter than that human hair we mentioned. If you force dirty oil through those tight spaces under high pressure, those microscopic particles act like liquid sandpaper.
Ouch.
They score the metal surfaces, creating even more metal shadings, and suddenly the equipment is destroying itself from the inside out.
Which totally explains why Clean Oil Services has a strict protocol to filter and verify all new oil before a single drop touches the machine. They process it until the particle counters prove it meets the original equipment manufacturer's required ISO code. But that brings up a really interesting physical problem.
What's that?
Well, if the new oil is dirty and the actual steel pipes of the machine have been sitting in a fabrication yard or have just gone through a major maintenance outage, you can't just put perfectly clean oil into dirty pipes.
Right, you just ruin the clean oil.
Yeah, because the sources mention things like mill scale, welding slag, and rust being left inside the system.
You've hit on the core challenge of commissioning new machinery. You cannot simply introduce clean oil into a contaminated environment and expect it to stay clean.
Yeah.
The fluid will immediately pick up all that leftover construction debris.
So my initial thought reading this was, doesn't a multi-million-dollar turbine have its own built-in filtration system?
A lot of people think that.
Right, like why not just turn the machine on, let the oil circulate, and let the onboard filters catch the welding slag? Why bring in Clean Oil Services with these massive external blue filtration skids, the ones branded EPT Clean Oil in the documents, to do this specialized job?
It all comes down to fluid dynamics. The normal, everyday operational flow of a turbine is what we call laminar flow.
Laminar flow.
Yeah, it's smooth. The oil in the very center of the pipe moves the fastest, but the oil right up against the inner walls of the pipe is barely moving at all. It acts as a protective cushion.
Oh, I see.
That laminar flow is totally incapable of dislodging heavy, embedded debris like rust or a chunk of welding slag stuck to the side of the pipe. Onboard filters are only designed to catch normal, everyday microscopic wear, not excavate construction debris.
So it's less like using a garden hose to wash your driveway and more like, well, think about how a slow-moving stream leaves the rocks in the riverbed completely untouched.
Yeah,
To
exactly.
actually carve out a canyon, you need a raging, chaotic river. You need
Wow.
turbulence.
That is a perfect analogy. You need to transition the fluid from smooth, laminar flow into chaotic, turbulent flow. In engineering, we measure this using something called a Reynolds number.
A Reynolds number.
Right. To get the shear force necessary to literally rip embedded debris off the internal walls of the steel pipes, you need a very high Reynolds number. And the turbine's own pumps physically cannot pump fast enough to create that turbulence.
So Clean Oil Services hooks up these mobile, high-flow EPT clean oil skids to artificially create that raging river inside the machine.
They do.
But wait, if they are blasting oil through the system fast enough to rip off welding slag, how do they keep from blasting that exact same chunk of slag straight into a delicate turbine bearing and just destroying it?
That is where the heavy engineering comes in. The sources detail a really meticulous workflow, starting with a deep side assessment and then moving into system preparation.
So they don't just hook up a hose and flip a switch.
Not at all. The technicians literally go in and unbolt the piping connections to all the sensitive components, the bearings, the tight clearance valves. They install temporary jumper hoses to bypass those delicate parts completely.
Ah, so they create a closed temporary loop. The oil rushes through the heavy main pipes, rips the dirt off the walls, and then bypasses all the fragile stuff, carrying the debris straight back to the external filtration skids.
Precisely. They engineer a safe, high-speed path, and they also manipulate the temperature.
I noticed that. The documents specifically highlight high-velocity flushing with temperature control. Why does heating the oil matter if the goal is just to move it fast?
It goes right back to achieving that turbulent flow. When you heat industrial oil, its viscosity drops. It gets it thinner, more like water than thick syrup.
Oh, so it moves more easily.
Yeah, and thinner fluid moving at high speeds creates significantly more turbulence and shear force against the pipe walls. It's a highly controlled, aggressive scouring of the system.
And they don't just guess when it's done. The final phase is verification. They literally don't disconnect their skids until their onboard particle counters generate a documented ISO 4406 report proving the pipes are microscopically clean.
Right, it removes all the guesswork for the plant manager before they press the start button.
But, it guarantees the physical dirt is gone. But physical dirt, solid particulate, is only one part of the battle.
Very true.
Because as we move into the oil dehydration documents, they introduce something described almost like a silent killer lurking in these systems: moisture, water contamination.
In many ways, water is more destructive than a chunk of dirt,
Mhm.
and it is vastly more complicated to remove.
The sources break down water contamination into three distinct forms, which I found fascinating. First, there's free water.
Yeah, that's the obvious one.
Right, that's what you'd expect, water that is completely separated from the oil and is just sitting as a puddle at the bottom of the reservoir. Then there is emulsified water, where the water is whipped into the oil, making it look cloudy, sort of like a murky salad dressing. But the third state, here's where it gets really interesting: dissolved water. This is water mixed into the oil at the absolute molecular level. It is completely invisible to the naked eye. The oil looks perfectly clear, but it's loaded with moisture.
And that invisible moisture is a catastrophic threat to heavy machinery.
I mean, I can easily visualize why a rock in a gear is bad. I can even see why a physical puddle of water causes rust. But why is molecular dissolved water such a lethal threat to a multi-million-dollar asset?
If we connect this to the bigger picture of how industrial machinery actually functions, it all comes down to the physics of lubrication. The entire purpose of that oil is to create what is known as a hydrodynamic film.
Meaning the oil essentially acts as a microscopic physical wedge holding two incredibly heavy metal gears apart so they don't grind against each other.
Yes. Because oil is a non-compressible fluid, it can handle thousands of pounds of pressure without squishing out of the way. It forms an unbreakable barrier.
Okay, I follow.
But water is compressible. And more importantly, water has a much lower boiling point than oil. When that invisible dissolved water gets caught in the microscopic load zone between two heavy gears, the extreme pressure and friction generate intense heat.
And the water hits its boiling point.
Instantly. It flashes into steam in a fraction of a second. This is a microexplosion called cavitation.
Wait, actual explosion.
The microexplosions, yes. When that water vaporizes, your hydrodynamic film completely collapses. That protective wedge disappears, and you get direct, violent metal-on-metal contact.
Wow, so even though you can't see the water, its physical properties are literally destroying the load-bearing capacity of the oil.
Exactly. But it gets worse. That's just the mechanical damage. Water is also a highly reactive chemical catalyst. Even at the dissolved molecular level, it interacts with the metal surfaces to trigger microscopic rust.
It's rusting from the inside.
Yeah, and crucially, it accelerates the chemical degradation of the oil itself. It breaks down the base stock and destroys the expensive chemical additive packages the oil relies on to prevent foaming or manage heat.
Which means when Clean Oil Services rolls in with these advanced vacuum dehydration systems to pull out the free, emulsified, and dissolved water, they aren't just drying the oil out. They are restoring the fundamental structural and chemical integrity of the fluid.
That's exactly right.
They are stopping that metal-on-metal cavitation before it happens.
They are extending the life of the machine. But you mentioned chemical degradation, and that accelerated breakdown driven by heat, physical stress, and water leads us to the final and perhaps most complex hurdle in these sources. What happens when the oil literally starts to cook?
Yeah, the documents refer to this as the creation of varnish. Now, when I hear the word varnish, my brain immediately goes to finishing a wooden dining table to give it a nice hard shine.
Sure.
But in the context of the filtration and conditioning services outlined here, varnish sounds like an operational nightmare.
It is one of the leading causes of unplanned turbine shutdowns globally. As oil degrades from constant heat and pressure, it undergoes an oxidation process. This creates what the industry calls varnish precursors.
Precursors.
Yeah, these are incredibly tiny, sub-micron soft contaminants.
So we aren't talking about hard metal shavings anymore. We are talking about soft, sticky chemical sludge.
Right. And the danger of these varnish precursors is that they are highly temperature sensitive. When the oil is hot, they stay dissolved. But as the oil flows into cooler parts of the turbine system, Those sticky precursors literally plate out.
They plate out.
Yeah, they drop out of the fluid and stick to the internal metal surfaces, forming a tough, lacquer-like coating.
And the sources point out this is uniquely devastating for hydraulic servo valves. These are the highly sensitive, incredibly precise valves that control the speed, the load, and the crucial safety actuations of the turbine.
They're the brain of the mechanics, really.
Right, and if that sticky varnish coats the inside of those tight clearance valves, they start to stick. You get erratic mechanical responses, or worse, a full system trip where the turbine just shuts itself down to avoid ripping itself apart.
A sticky valve in a system handling massive high-pressure steam or gas is a critical failure.
Let me play devil's advocate here, though. If the oil is chemically cooking, if it's breaking down and literally transforming to sticky varnish that threatens the whole machine, why go through the trouble of conditioning it with specialized equipment?
It's a fair question.
Like, if the oil is that far gone, why not just drain the entire reservoir, dispose of the bad oil, and buy fresh oil?
It's a totally logical question, but it hits a wall when you look at the scale and economics of heavy industry. We're not talking about draining 5 quarts of oil from your driveway into a pan.
Right.
A large steam turbine or a central hydraulic system can hold tens of thousands of gallons of highly specialized, incredibly expensive lubricating fluid.
Okay, so the upfront capital expense to buy 10,000 gallons of premium turbine oil is massive.
Immense. And you also have to factor in the downtime to drain and refill it, the labor, and the astronomical environmental cost of safely disposing of 10,000 gallons of degraded hazardous waste. It is a logistical and financial nightmare.
So how does conditioning solve that? The sources mention that Clean Oil Services uses advanced chemical conditioning to restore the oil's solvency. What does restoring solvency actually mean at a chemical level?
Think of healthy oil as a sponge. A clean sponge can easily absorb and hold on to water. In the same way, healthy oil uses its solvency to hold on to its crucial chemical additives and keep microscopic contaminants suspended so they don't stick to the metal.
Okay, I'm picturing the sponge.
But when the oil oxidizes and fills up with those sticky varnish precursors, the sponge is full. It can't hold anything else.
And that's when the varnish drops out of the oil and plates onto the servo valve.
Exactly. By deploying ultrafine particulate removal and advanced ion exchange conditioning, Clean Oil Services is essentially wringing out the sponge. They physically extract those submicron oxidation byproducts from the fluid.
Oh, wow.
When you remove the bad stuff, the oil's natural solvency returns. It can hold its additives again, its viscosity normalizes, and its thermal stability is restored.
So they aren't just filtering dirt. They're essentially reversing the aging process of the oil. They are rescuing the asset.
They are. By conditioning the fluid instead of replacing it, they extend the life cycle of that oil indefinitely. That optimizes the plant's maintenance budget and drastically reduces the environmental footprint of the entire operation because you aren't generating thousands of gallons of waste oil every few years.
So if we take a step back, what does this all mean for you, the listener? Why should you care about turbulent flow, dissolved molecular water, or the solvency of turbine oil?
It's a valid question.
Because even if you don't personally run a power plant, a petrochemical refinery, or a heavy mining operation, this exact discipline, what the industry calls reliability-centered maintenance, is quite literally the invisible framework of modern life.
It really is.
It is what keeps the lights on in your city when the power grid is pushed to the brink during a heat wave. It's what keeps the massive cargo ships and rail networks moving so supply chains don't collapse. This obsessive microscopic level of contamination control is the ultimate safety net for the infrastructure you rely on every single day.
It is the absolute bedrock of industrial reliability. You can engineer the most advanced, robust mechanical systems in human history, but without pristine fluid transmitting the power and protecting the moving parts, that machine will ultimately destroy itself.
And as we wrap up our deep dive into these sources today, I think that is the most profound takeaway. The materials from Clean Oil Services and their integration with millwright and commissioning teams prove that in the world of massive, heavy steel industrial power, the biggest threats are almost always microscopic.
Without a doubt.
Whether it is engineering a custom bypass loop to aggressively power wash welding slag out of a pipe, or using high-tech vacuum dehydration to pull invisible dissolved water out of turbine fluid to stop cavitation precision, is absolutely everything.
It is a constant, quiet battle against degradation. And looking at these sources leaves us with a rather profound final thought to ponder. We've just spent this time exploring how multi-million-dollar heavy steel machinery can be completely derailed by a few microscopic metal particles or a single drop of dissolved water.
Right.
As our world moves rapidly toward fully autonomous AI-driven infrastructure and even more sensitive, tight-tolerance automated physical systems, how truly fragile will those future systems be if even one microscopic variable in their maintenance is overlooked?
That is an incredible thought to end on. I mean, a heavy piece of steel failing is one thing, but an AI-driven, hypersensitive, automated grid, the margin for error is going to shrink to absolute zero.
Exactly.
Thank you all for joining us on this deep dive into the invisible, high-stakes world of industrial fluid management. We highly encourage you to keep questioning how the complex machinery around you actually works, and we warmly invite you to bring that curiosity to our next stack of sources. Until then, keep diving deep.